I'm going to talk about things that scientists don't talk about very much. When we go about doing any kind of activity, we make assumptions that we never talk about. We just go about do the activity. And there's a field of scholarship called philosophy. Philosophy, this is a great definition of it. We question and we try to understand the common ideas that we use every day in our activity, like science, and we don't think about them. We just do it, okay? These ideas are always problematic, and philosophy is dealing with those problems. Other definitions of philosophy that I like are providing lawyer-like answers to childlike questions. Little children aren't afraid to ask important questions. We get afraid through our education system. This has kind of been my hobby for decades, and philosophy's gotten a lot of bad raps in the current situation. Here's a governor of North Carolina, worthless courses, no chance of getting jobs. Here's little Marco, more welders, less philosophers. But we have issues in our science. We commonly view, and this is a dictionary definition, and this is the etymology of the word, science as knowledge, as a body of facts or truths that we arrange systematically and we assume are associated with general laws. Now, obviously, these are things we deal with, but there are problems with this, and these problems are coming out today. The most recent word of the year, chosen by the Oxford English Dictionary, is post-truth. Post-truth is a hallmark of our time. So here we have some well-known philosophers, Plato and Descartes. And we have some individuals who have different views about this concept of truth. But I think there's something more fundamental than this argument over truth and facts. And this doesn't get played enough in our discussions. Because what we're seeing is what's called fake science. You've heard of fake news. Well, fake science is not really about fake facts or factoids, which is the better word for it. It's a fake attitude, because it is not about the goal of honestly seeking for the truth. It is about utilizing your concept of truth for power, money, fame, influence, re-election, whatever. Okay? That's what it's about. It's about an attitude. Scientists themselves are not immune from attitude problems. They may have goals that are more directed at other things besides this honest, total, absolute dedication to search for truth. So a better definition, science as an activity, attitude, it definitely involves a community of like-minded investigators. There's no science that's done by one person developing ideas. It's just community. And they're passionately driven by this inquiry into nature, or more broadly, inquire into reality and the actualities of the world. Actually, in science, we need uncertainty. If we were certain of things, there would be nothing to investigate. So we like uncertainty in science because that allows us to learn new things. It's a living, dynamic process of inquiry. It's open-ended. And our product is not facts and truths. It is reliable information. So science is not facts, it's acts. And we're not making the best use of it, thinking of it as knowledge. And this is, of course, going to get into the policy arena, because there's a general assumption that we're going to have truths or at least reduced uncertainties, and that is the basis for our actions. Now, I'm going to question that. Remember, philosophers are questioning fundamental ideas. I'm going to suggest that science as a process of community is to provide a continually updated guide to action. Continually updated. That means we don't know for sure. Remember, the hallmark of science is experiment. We don't know. We learn as we go along. Who would get elected saying they don't know the absolute answer, or they don't have a bunch of experts to tell these things? Who would get elected? You have to claim a false claim that you know what the truth is. If you say, I'm going to do experiments, they're not going to vote for you. But if you don't think of everything as an experiment, you are not a scientist. Scientists have to think about reality. So why is science action thinking important? The world is changing. It's always changing. Now we talk about prediction. Accurate prediction of the future is impossible. There is no way to know what those complex changes are going to be. Prediction, which we use in science, as basically a logical deduction from assumptions, is a powerful tool for our thinking. But we misinform the public when we say prediction, because they think that's saying what the future will be, and that is wrong. Okay? Science is being misrepresented and misunderstood. So we have this in the decision-making, the policy formulation area. We don't believe science because it has absolute answers. We believe science because it is a thing that works. It eventually finds interesting things. It is a guide of wisdom to what we're doing. But we have made a mess of the communication by making this thought that it is providing an absolute basis for doing things. Now I'm going to talk about some natures of inference, and these get into pretty heavy stuff, okay? We generally think of the modes of thinking, our modes of inference, as inductive and deductive. There's a third mode of inference. It's called abductive. The source of this goes back to Aristotle and the prior analytics, okay? And we're going to say a little bit about that, but it's a big topic. I want to make a little side discussion in regard to hydrology. Conventional hydrology evolved out of a connection between science and engineering. And science and engineering they're kind of like two children that were, born to deal with the world, and they have different approaches. They each have their proper role, and they also rely very much on one another. People have talked about this. Jim Doog, the late Jim Doog, talked about it in a number of his papers. This was one attempt where he made to try to emphasize the difference. Engineering, for him, was utilizing prediction as a tool to achieve control, to achieve designs. Science, of course, is using prediction as a tool because ultimately it's trying to produce understanding in regard to the world. Engineers utilize the formulas of basic scientific understanding, but they're generally not trying to discover new things about the world. They're trying to cope with the limitations of the world to make things. So you have a limitation of air that is very difficult to get heavier things to fly through it. You overcome those difficulties. whereas scientists are interested in the fundamental properties and the processes of the air, of the atmosphere, because they're curious and they want to know how nature works. So engineers will design a system. They know, good engineers know whatever they design is limited in time and space. They can't deal with the whole complexity of the world. Facts are constrained. That must be, they offer constraints. You have to overcome facts in order to get things done. It's all about achieving the result. Science, we want to learn the truths nature has to tell us. Nature is viewed as the source of that truth. Nature is essentially the object of our worship because we want to get at what nature is presenting to us. Facts are the tools in our inquiry as we are seeking that kind of truth. So in engineering, we employ many of the same kinds of models that are used in science. We employ the same words, we employ the same concepts. But in engineering, we seek the applications of current understanding. And in order to achieve the best designs, we want to reduce the uncertainties that we have to face. But in good engineering, we know that those solutions are severely limited. The world is always changing. So the system that we may have formulated is not the one that may apply in some future time and under some future circumstances. So there can be unknown factors, changing conditions that are going to bring about problems in what we thought. Well, those are exactly the sort of thing that science as action is trying to figure out. But we're not talking about science as what's in a textbook. We're talking about the stuff we don't know that we're continually trying to work out. Okay, so I can't give you a full course in uncertainty, but I'll give you a famous exposition of uncertainty. Here's a Secretary of Defense under a previous administration, and he's giving you the short course on uncertainty. There are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, there are some things we do not know. And we also know there are unknown unknowns. These are the ones we don't know we don't know. Okay? So we actually divide these modes of uncertainty. So the unknown unknowns are aleatoric uncertainties. They are the things that we can deal with statistically. They can be quantified in a straightforward way by inductive reasoning, which calculates probabilities. Now this, of course, this calculation of probabilities was invented by French mathematicians. It was invented in the 18th century. And it was invented so that bored French noblemen could do well in gambling, okay? So it's really based on card games and situations like that, which are mathematically tractable. And this was a fantastic discovery, because before then, there was no way to deal logically with uncertainty. But there are also the things that could be known in principle, but we just aren't able to know in practice. Those are very problematic. That's epistemic uncertainty. There's a problem, though, with this whole thing. And it's fascinating that nobody realized when Rumsfeld was pointing this out, that he's talking about three factors, or three different things, and he's got two elements, known and unknown. There really should be four parts of this. So you have known knowns, you have unknown unknowns, you have known unknowns. There are also unknown knowns. He didn't mention those. Unknown knowns are actual realities, possibilities of which we are unaware. Why are we unaware of things that are known? We're unaware because of ignorance, incompetence, deliberate deception, a whole variety of reasons. These can be known, but they're treated as unknown. We'll come back to that problem. So let's talk about induction and deduction. Everybody knows what these are. You learn about these things. Induction, you generalize from individual observations to general conclusions. For many logicians, induction is just all kinds of uncertain reasoning, because deduction is absolutely certain if it's done correctly. If it's done correctly, you do not make a mistake with deduction. It gives certainty, but it only gives certainty relative to the assumptions you start with. Deduction does not give you anything new. You start with assumptions, but it preserves truth all the way through. And of course, the hallmark of a deductive system is mathematics, and that's why mathematics is powerful. It's true. It's always true if you do it right. However, what is it true to? Okay, that's the problem. Now, we have very powerful uses of mathematics in our science, because we can define what's called a system, structured set of objects and interactions among those objects. And we can utilize deduction to predict the parameters from the system. And then in sort of classical science terms, we would try to compare those predictions to measurements, to some measure of the real world. That's an inductive process, because we're looking at specific things. And then we have this idea that we can verify or validate these predictions, and that somehow will provide the basis for our future action. This is where the problem comes in, because physicists have long known that the way in which you do that is you have what's called a controlled experiment. An experiment where you have all of the relevant variables of your system under complete control. You don't have extraneous stuff going on. Okay? You cannot put the Colorado River in an experiment box. Okay? That's not possible. Most of the interesting things we're interested in hydrology, we can't put the whole thing. We can't put the Earth's hydrological cycle in an experiment box. So we can't do controlled experiments in an absolute sense. And there are also pure logical problems with this. And I don't have time to go into them. It's one of these logical problems is called the underdetermination of theory by data. That was worked out by what many consider to be the most important logician of the last century. William von Orman Quine was one of the people that pointed out the underdetermination of theory by data. So in deductive science, we presume features to be relevant to our idealized phenomena. So we have timeless laws of physics, we have boundary conditions, we have systems parameters. There's a good reason why physicists love Occam's razor. Simplicity is key if you want to have control on your system, because then you reduce the number of variables that can go into your controlled experiment. So those for whom theory is the main goal in their activity, they can deduce idealized properties of phenomena, and then they attempt to test those by correspondence, the correspondence of our concept with a measurement, or with what we what we find in the world. But as I said, there's a logic problem that's been known for 50 years at least, called the underdetermination of theory by data, which is that there are always secondary assumptions that are involved, and many of which you do not specify. And those may explain an experimental result. Either a failure of the experiment to confirm, or a falsification. It can be falsified for the wrong reason. So the devastating conclusion of this is there's no way to actually verify or falsify a conclusion. Well, I'll point out that this has been the subject of a recent debate in the journal Water Resources Research. So if you look up on the online version of that, you'll find a series of accepted articles, just accepted, on hypothesis testing in hydrology. And Günter Blursch is the overall moderator of this. And you have a bunch of folks, including me, pointing out some of these issues. So I gave this provocative word, which people don't recognize. Look it up. It's an English word, Uberty. It means fruitfulness. It means science that is exciting, discovering stuff, etc., as opposed to worrying about certainty. Productive, creative ideas. How do we do that? That's really absolutely critical in science. So as Dirty Harry said, a man's got to know his limitations. So one of our limitations is there's a lot of irrelevant philosophy out there. It's one reason why I study philosophy. A lot of philosophy of science is really bad. It's done by philosophers who've never done real science. And they talk about logic and lots of other things, but it is pretty worthless. A whole branch of philosophy developed called logical positivism or logical empiricism that basically is the only branch ever to go away by its own criteria. They falsified themselves by their own criteria, although many scientists don't know this, and they still go by these kinds of things. So anytime we model a system, we are simplifying assumptions. I've already mentioned prediction is a logical construct. It's not a prophecy, at least in terms of the way we use it in science. Verification is logically impossible. And we tend to allow, as scientists, our output to be used as authority that people would take as a basis for action. Albert Einstein once said, "All my life I've questioned authority, and in punishment for this, in my later life, they've made me an authority." Okay? It's a wise comment about problems we have in science. So let's move on to some of the big problems we have. Okay, here's Nassim Taleb. He has mostly written about economics, and he started what was called the black swan theory, or the theory of black swan events. It actually is a thing that goes along with inductive inference, because philosophers had always liked to say, well, the validity of inductive inference is we have these things in the world, and just by observation, they're all of a certain type. So we're here in England, and we have swans, and they're white, and we go to America, and we find swans, and they're white. So all swans are white. Even though it's not a valid deduction, it seems very reasonable until they go to Australia, and they find a black swan. Okay? So these are surprises. And they don't fit. They are outliers outside the realm of regular expectation. The ones that are important are extreme impacts. The recent 2008 financial crisis, big surprise, huge impact. And human nature makes us try to explain these things. So Taleb is making thousands of dollars for lectures going around talking to economists and others about this. Okay, another thing we have, and comes from social scientists, wicked problems. These don't have definite formulations. They don't allow you to claim success, so politicians are really unhappy about this. Politicians love to claim success. That's how they get elected. They typically don't have solutions that are true or false. They may be good or bad. Often they are unique. The circumstances don't fit into generalities. Many times there's multiple explanations that seem to fit these sort of things. So they don't fit into the textbook as to how these things work. So what are we talking about here? So here's a young lady who happened to live near a nuclear power plant in Japan, and she is being checked for radiation. Talk about human feeling. Being exposed to radiation. This is something that goes on for decades. It was a big deal in Japan, where the first nuclear bomb was dropped. So this is a big deal. What happened? In 2011, we had the tsunami. Blame it on the tsunami. Blame it on nature. But what happened? What was the wicked problem? More than half of Japan's energy comes from nuclear power. And the Fukushima Daiichi nuclear plant was built on the northeastern coast of Honshu. Tectonically, Japan is an uplifted island. There were uplifted marine terraces. They cut into the marine terrace so they could put the power plant as close to sea level as possible. Why? Because it costs a lot of money for the cooling water to go into the reactors. So it was decided that the efficient thing to do was to put that power plant down low and then build an appropriate seawall for the largest size tsunami that could be reasonably envisioned to protect against that tsunami. So that's what they did. They put all this infrastructure down there, and then they built a massive seawall and figured that was going to take care of things. So they had a big tsunami. This is Minami Sanriku, which is a town that was heavily devastated. Here's the tsunami coming in there. Here you see these people here. They are on the top of a 3-story emergency tower shelter. That was designed for the people in the middle of the town. Because the tsunami was so close offshore, there was between 30 to 45 minutes warning time. So the Japanese people are very well organized. They knew they could get to high ground like that high school. But in the middle of the town, you had a problem. We can't run fast enough. So they had this tower. These people on the top of the tower, the ones here were all killed. The only people that survived were these 2 that climbed the radio antenna that stuck up above the 3-story high tower. The tsunami wave was bigger than the largest thing that they could imagine in the whole process. But it was an unknown known. It was an unknown known. But we'll get to that point. How did they calculate how this tsunami wave was going to be? They used inductive and deductive reasoning. They used a probabilistic seismic hazard assessment. Japan has lots of earthquakes. You have lots of data on earthquakes. You know the sizes of earthquakes, so you can do a probabilistic analysis. Then they estimated what was called the probable maximum earthquake, the biggest kind of earthquake that they could imagine could occur on this fault system. And they created a tsunami generation scenario for that probable maximum earthquake. And then they computer modeled the propagation of the tsunami wave from that source, taking that mechanism, and of course this wave is going to refract as it comes in close to the power plant. So they did a prediction of the tsunami run-up height in the area of the power plant, And they calculated that this maximum probable earthquake and the maximum tsunami that could be generated would produce a 5-meter high wave at the plant. So they added a factor of safety of 0.7 meters, and they got a 5.7 meter high. They were so sure of this that they had the emergency power generators at the level of the seawall, because they felt the only problem would be something maybe electrical or something like that. The March 11th tsunami wave was 15 meters high. This isn't a little mistake. This is a catastrophic mistake. And it is an unknown known because the answer is out there known. The problem was wicked because it led to tremendous issues. Rumsfeld, in not recognizing this, led to the Iraq War. Estimates are it'll cost at least $1 trillion, and the subsequent problems in the Middle East, still ongoing, are related to that. Now in Japan, this was the largest dollar damage so-called natural disaster ever. Hundreds of billions of dollars, because it closed down the entire energy structure of the Japan. And it was completely preventable. So if you go to the High Country News, the recent article about the West's superfloods begins with a mention of a Japanese scientist, Koji Minori, very humble person at Tohoku University, a paleontologist, studies fossils. He was intrigued by an old manuscript that said that a giant wave had destroyed a castle town and killed about 1,000 people in 869 AD. Now he's a paleontologist, so he thinks about this, and he goes and, well, first of all, he looks up what this was. Earthquake, 869. The exact date can be figured out because they kept good track of these things. He figures, well, if this went across this Sendai Plain, which is right near where the power plant is, it would leave evidence because the marine shells from the shoreline would be carried inland. So he went there, dug holes. So here's a picture of the actual tsunami coming across the Sendai Plain on March of 2011. They dig holes and they find that white stuff mixed in with the organics of the shells that have been washed up. The 869 tsunami went 5 kilometers inland. They published the paper in 2001 in a Japanese science journal prominently. So here's Minori. Here's his plots of how the tsunami wave came in. And they estimated that this was a 1,000-year event and that it had a magnitude associated with a magnitude earthquake of about, I forget the exact number, 8.6. The 2011 was a 9. And that it would produce this kind of height of wave to generate this. A unknown known, but only by Tokyo Power and Electric and the people that did those calculations. So there are certainties that we can figure out. We can know that what has happened absolutely certainly can happen. There are certainties that we can work out scientifically. This is not about probabilities. This is a different kind of science. This is not something that the public can be mystified by, because they're mystified by things like the 100-year flood, which has nothing to do with real years and nothing to do with real floods. and depends on a ludicrous assumption that this could communicate to the public. This is a stone. It is in a little village that had a tsunami wave height of 40 meters. We went there in my research. There was a picture of me with a train that had been knocked off of its tracks in one of those towns. This was done 100 years ago after a tsunami, and it basically says to the villagers, don't build your houses below this point, and has religious significance. And the people in this little town ignored what the government told them. They built their whole town above that level. Nobody was killed. They had nothing but fishing villages and fishing equipment and a campground where the village used to be. And they followed that, and they had no problem. So this is about what nature is telling us. And it is, as opposed to what we as scientists act like experts and are saying how nature is supposed to be. We can easily be painted as one set of experts, and those who don't like that will get their set of experts, and you have an argument. And the folks in the anti-science realm are experts at this. They're trained as lawyers. There is no argument with nature. Nature just is. And if you go against that, you are going against reality. And that's a very important point when we're communicating. Ultimately, Tokyo Power and Electric resisted this. They wanted to say this was beyond the realm of possibility, but eventually they actually had to say that they were in error. They had been given the information about this event, and they sat on it and didn't act on it because of the way they viewed their understanding of the problem. Biggest disaster in history. Okay, so abduction, and I said this is a big topic. This is where we use evidence, indicators, signs, traces, fossils, you name it, that show real phenomena, and it involves discovery. It involves not theorists, but investigators. Investigators who are trying to discover things about the world. And the process of thinking is a lot like a detective. You try to infer the conditions that would bring about those phenomena. So if you have a master detective like Sherlock Holmes, they do not go into a crime scene saying, I have a theory about how crime works, and I'm going to test my theory with these things. No. Sherlock Holmes goes into the crime scene, and they look for odd things. Why? Because Sherlock Holmes knows all about crimes. He's been involved with it. He knows when something is odd, it's a little strange thing, and he picks up a piece of tobacco. And then he knows that this piece of tobacco was only bought at a particular shop in London. And then he knows that he can see how many people go to this shop. And then he can go to some other clue, like a shoe print. And he can see that there's only so many places that would produce this kind of shoe. He can look for dirt that has been brought in from another place. So you all know how detective stories work. It's a whole set of interactive things that you think about that allows you to put together what happened. So you're reasoning to a particular case, you're reasoning to causes, but you're not doing this in some simplistic kind of way. You're doing this in a very sophisticated way, and you're not testing by correspondence of your particular concept to one observation. Instead, you're utilizing consistency, coherence, and a thing called consilience, which I'd have to explain, that basically relate to the causative structure of what you're dealing with. And this actually, some philosophers have talked about. It's called causal overdetermination. And it is that when something happens in the past, you're not dealing with some odd little things. The people who study things that are related in the past know that some phenomena, and particularly a huge catastrophic phenomena, has effects that are emplaced all over. Think of a volcanic eruption. It throws tephra over, in big eruptions, thousands of kilometers. And you can find the signature of that material all over the place. There's a tremendous amount of evidence of stuff that has happened in the past that can be related to the causative structure of those things. So here is a structure of scientific thinking, and this isn't by a geologist. This is done by an artificial intelligence guy. John Sawa was one of IBM's top computer scientists. He is now retired. He was an expert in logic, so he understood completely what deduction and induction are about. But he recognizes that the process of science has to have the investigative approach, because what we make as our prediction that we try to match against the world, never going to be totally a verification. We have to learn from that process. So this process of induction is our measurement process, where we're looking at this and we're building this vast set of knowledge. This is the stuff Sherlock Holmes comes to the crime scene with. But then abduction has to be used. Abduction is the looking at the odd thing, the anomaly, recognizing that that may be significant, inferring the conditions that would bring that about, and those then become a working hypothesis. Not just hypothesis, working hypothesis. And you may have multiple working hypotheses that you employ to generate new possible theory. Hypotheses are our tentative theories. Actually, because we never know that our theories are absolutely true, they're always a kind of hypothesis. Now, we don't dispute that if we step out of a multi-story building, we're going to fall to the ground, because gravity is a really good theory, okay? We don't dispute that. But we're never absolutely sure, because we never can get full evidence. And of course, Einstein discovered, under the circumstances of the whole universe, that gravity is more complicated than the way we thought. Well, I'll say a few things, because we're running out of time here. We've got big problems. The whole southwestern U.S. is dependent on this river system, the Colorado River system. And we have had a lot of issues of late where we've worried about drought, okay? Well, California has worried about drought until recently. So if you go to the same article that just came out in High Country News, you will see the discussion of California's highest dam. And that reservoir, which was nearly empty, filled. And people suddenly learned something about dams and reservoirs. That is, they're not designed to protect you against all floods. They are designed to protect you against little floods. Now, how many dams would be built if the people who built them were to say that? But I am telling you an absolute truth, because every dam is built under circumstances of limitation. We cannot build the dam for all possible floods. We have to pick a point at which we build it. And we put spillways on dams for that emergency. And these spillways are not tested. So here is the major spillway, here's the ultra emergency spillway. Both of them were in a state of possible loss. Fortunately, nature didn't produce that loss. But our Colorado River in 1983 nearly lost the Glen Canyon Dam. So here's the Glen Canyon Dam does not have a spillway that can carry the full capacity of the probable maximum flood. It has an underground spillway. And in 1983, that spillway cavitated and eroded, and if the water inflow had not stopped, we would have lost the Glen Canyon Dam. Now, for drought conditions, you want your reservoir full. But for floods, you want your reservoir not full. So there's a big problem. If we want to protect against that future drought, we also have the problem of the potential of flood. And the potential of flood, if it takes out the Glen Canyon Dam, or the Hoover Dam, which is just had an anniversary, it was built in 1936 or 37. I mean, these dams are getting old. Okay, if you lose those, the drought will seem like nothing, because you have lost the whole water capacity of the system. So this risk, we need to understand. And we don't have, if you look at the gauge record for the Colorado River, it's ludicrous. It doesn't give you enough information. If you want to worry about a chance of a 1,000-year flood, you don't have that information. So this is a paper my colleagues and I did a couple of years ago. We had to fight to get this in because we dig holes and we look at sediments. We don't run models. But what we found was that near Moab, we had flood stages 15 meters higher than the normal river stage, and we had 2 exceedances in the last 2,000 years of the calculated probable maximum flood. 2 exceedances within the last 2,000 years. And the probable maximum is supposed to be the largest thing that nature could produce. So there's a big problem. And there's a lot of, and it's also an unknown known, because the information on these extreme large floods is just a matter of going out to nature and looking for it, because it's there. The sedimentary deposits are there. The whole thing is there. And minuscule resources have been spent on that. Okay, there's lots of other problems, and I want to leave time for people to take jabs at me. But we've got lots of problems. In regard to disasters, politicians love disasters. They get to go and pass out money. And so that's a big problem. We have a regulatory problem. Everybody's treated equally ignorant of the hazard and their personal responsibility relative to it. We have a science effect in that most of the support for science comes as a byproduct of this ignorance. So the money flows because of this. And we as scientists want the money, okay? So this is a kind of an ethics question. There's lots to say about how floods cause damages, political opportunity, money flows to have people rebuild, creates more opportunity. It all goes around in a big circle. And the scientists are part of this. So in my paper that was just published, I've got a table comparing theory-directed versus world-directed investigative approaches. And you can go point by point in terms of the kind of science that's done and look at how these are done differently. I'm not saying that one is better than another. I am saying that we have invested huge amounts of resources in this one and almost nothing in that one. And if we really want to achieve things of making a change in the dysfunctionality of the relationship of science to policy, to politics, everything else, we need to think differently. And we need to think creatively. And this is one of the ways in which we might be able to do this. So, knowledge, well-justified true belief, that's a philosopher's definition. That is a thing. That is not science as action. Understanding is a process involving relationships of the knower to the object sufficient for intelligent wise behavior. It's a process. Yes, that's science, science in action. Policy is an ongoing commitment to action, and it is a process. It needs number 2. We're only doing number 1, and that is causing problems. So that's philosophy. That's questioning fundamental assumptions. And the way that philosophers deal with this is they don't ignore it. They have dialogue. They talk about it. They try to work it out. And they talk about the things that are not comfortable to talk about. So that's what I've been doing. Thank you for listening.
So, Vic, we've built a technocratic society around the premise that science is number 1, which leads to number 3.
Mm-hmm.
And we built an entire culture around that.
Of course.
Certainly in the Western world. So, how do we go about changing that culture, which I'm sure our anthropology colleagues will tell us is not quick?
Well, I've been thinking about that too. And I think one might start with the issues that are most problematic with that assumption. And I think the most problematic issues are the really extreme events, because that's the part that the traditional way can't deal with. When the former President George Bush was confronted with Katrina, he didn't know what to do immediately. He thought, well, I'm just going to have Brownie go there and we're going to pass out lots of money and everybody's going to be happy. Well, it turns out that was a wicked problem. And he suffered badly. The usual pattern didn't work. And we're going to see this more and more. We're going to see huge, calamitous, disastrous things. Politicians are going to try to blame it on nature, or worse yet, they'll call it an act of God. I mean, this is ludicrous. And these are, as it was said long ago, these are acts of man. These are caused by people. And they don't want to hear that. But I'd say that is the opportunity for science to possibly interject and be able to get something different happening, because obviously changing the current way that things are done is a daunting task. It is built into the system. It's built into how the money flows to us in science. But we do have to think about what's going wrong, because to me it seems like things are just getting worse.
Along those lines, do you feel like there's an event that's going to be big enough that's going to spur on change if these events haven't done so already?
Well,
what's it going to take? Because we don't change till we get to the bottom, right?
There's all kinds of things that are out there. I was in a series of, there was a educational film producer who was trying to bring attention to flood problems. He actually interviewed me. He said, where are the next biggest flood disasters going to be? I said, without question, New Orleans was going to be the biggest disaster, because, I mean, the French founded it in 1700 on a levee. It flooded the next year. I mean, you could not build a city in a more flood-prone place. So New Orleans can get flooded from the sea. It can get flooded from the river. So the other big places, South Florida, right where a certain person has his big palatial place. I mean, that is a prime, big tropical storm hit location. Maybe there's some justice in the world. But, but the other one, another one is Sacramento area. They almost got it from an atmospheric river this time. When they get a good atmospheric river in there, you're going to see multi-hundred billion dollars of damage in that California site. When we're talking multi-hundred billions, as they say in Congress, you're talking real money. The whole defense budget, essentially. That will be a wake-up call. When that happens, there will be a lot of hand-wringing. And so maybe this is a macabre thought, but there's an opportunity, and as scientists we need to be ready to it. We need to be able to communicate more effectively, and our ally has got to be nature and reality itself. Not to think we're going to have arguments in the little games that are being played, that are being defined by the political entities.
Tim?
Yeah.
What do you think about, I guess, improving our understanding of these kinds of situations when even nature itself may not be representative? For example, you were talking about the flood deposits from the Colorado River in Moab, Utah. If because of climate change, the potential for, because of climate change and non-stationarity, couldn't that potential for flooding actually be changing, which could further increase our uncertainty for trying to assess the risk of the Colorado River and the potential it has for dams and water storage?
Spoken like a good engineer, okay? I have seen this comment for decades, okay, in regard to paleoflood hydrology. It's not a scientific comment. It is a comment about uncertainties. And it is valid. The paper that I cited, that we published in Water Resources Research, got that comment. And so you go to the paper, you will read the part I wrote as a response to that comment. The science is about asking the right question, not about having the absolute answer. The right question is what nature presents to us. So here's the question. Are the storms of the future going to be totally unlike anything in the past in the nature of meteorological events? Now, you asked about climate. Floods are caused by meteorological events. They are caused by storms. Climate is related, but it's average conditions, okay? Droughts, for example, very much involve climate because they're a multi-year phenomenon. Floods are events, and events are generated by meteorology. And so you need to understand those, and so a question about the future. Is it going to be that we're going to create new kinds of meteorological phenomena that have never occurred before? We have that in bad Hollywood movies, okay? But or are we instead going to move air masses around and shift storm tracks? In which case, we have evidences of those past floods under those conditions from the past. So to say that because of non-stationarity, which has to do with statistical distributions, that is invalidating the study of the past, is to say that the past is worthless, that all we can do is just project in the future with this problem of complete inability to say what the future is going to be. Historians would roll in their grave. I mean, they have tried to figure out how human beings are going to be in the future, and it's all based on human nature and the habits of human beings. Do you not think that nature has habits and they're going to adjust? Climate is going to be just a shift in the characteristics of those habits. And the past is an immense reservoir of possible understanding. I fully admit that we don't have enough information about the past because it's been done by a limited number of people to solve that. But it is a unknown known. The information is out there if we could get it. Yeah. So anyway, okay. So
no one's a bigger fan of the past than me, although you can argue if you want. But floods of the future, you're absolutely right, are affected by circulation change. But the atmosphere is also getting warmer and warmer in an unprecedented way. And sure, you can go back to the Cretaceous or some other time to find a really warm atmosphere. But it's pretty clear from theory and observations, as the atmosphere warms, it holds more moisture. And when the storm does occur, the odds go up that it can dump more water per unit time. So in other words, there is an element of truth to this non-stationary aspect. That doesn't invalidate looking at the past to understand where these storms can hit. But we somehow have to keep in mind that we can create stronger storms. And another example of this would, of course, be atmospheric rivers. They would also be maybe convective storms, but certainly hurricanes.
And that seems to be where the theory is going now. And we might not have seen one of these warmer atmospheres since, Eocene. And so the geologic record of floods in the Eocene might be really hard to utilize for the current problem that's emerging, because there's just so few of them left in the rock record.
Yep.
How do we deal with that?
Well, first of all, you are making a theoretical projection. Yes, the atmosphere can hold
there's a lot of
can hold more moisture. That's true. But my question was not the generalities of the moisture that would be held in the atmosphere, but making a completely different kind of storm than has ever happened. And the only way we can know about that is to go to nature and check. Do we have really horrendously bigger floods than anything that is happening?
Well, you can see observationally evidence for this theory in the sense that in many parts of the world you're getting more intense precipitation.
Are you getting bigger floods than have ever happened before?
Not floods necessarily.
People are saying that they're saying, for example, in Britain, it was claimed after some of the recent flooding that this flooding was unprecedented. There's huge records that show no way. It's not even close to what's happened in the past.
No, you and I have talked about this, and I agree with you that we haven't seen it in the floods yet, but you're seeing it in the precipitation.
But are you seeing it?
In the room,
Are you seeing it in the most intense precipitation?
Yes.
But how long are our precipitation records that we're comparing it to? We don't have long precipitation records. We don't have long event precipitation records. We have long flood records. We don't have long event precipitation records.
But you got to be open to the fact that here's what you're arguing is essentially we have to look in nature for things. We shouldn't be blind to what nature is telling us.
I'm making a bigger argument. We have to look at the only reality we have.
But that includes short precipitation records.
Yeah, but we don't have long. We do have long extreme flood records, and extreme floods. People are concerned about what extreme floods will do. This gets into the communication problem. Telling people you as experts are saying this is going to happen is very different than saying this really did happen, and we can show this is what nature really did. That has a power that isn't something of expert scientists is saying this is the case. There's been lots of stuff done against the scientific experts that have tried to make cases for this because it's going to cost a lot of money to do something about
But are
it.
you saying then that the geologic record that you've looked at, and I don't know how long that is, but I know it's many thousands of years, contains the full range of Earth system behavior?
No, but it contains a better range of things than what we can imagine so imperfectly with our saying how nature is supposed to be.
I agree with that, but when it comes to precipitation, I want to find the longest precipitation record you have.
Precipitation is the wrong thing. We don't have the.
We did it. I think you guys have just about exhausted that.
But it's fun. This is what Vic's all about. You got to argue with Vic or it's no fun.
Buddy, I used to have lunch with Vic. On the order of once a week. We would talk about Charles Sanders first, so I'm familiar with what it's like to argue. I want to quote somebody who haven't put it so far. That's Lawrence Stern, who said every man has his hobby horse. So I have a hobby horse. It is different. And it is that, yeah, granted, I'm no argument about the points that you've made so far, but you have left out our ability to project imperfectly the consequences of a more active atmosphere, a hotter atmosphere, and so on through computer simulation. And I think that, and in fact, that's what atmospheric scientists are doing.
Of course, there's a lot of resources going into that.
I know, so I'm making my speech now. You've already said this, but I'm going to repeat it. We need all dimensions of science in order to address the problems that we have in the future. And computing and computer simulation are two of the tools that we have that really will allow you to address some of the questions that Beth is asking. Now, you're never going to be able to get the initial conditions, the boundary conditions exactly right, but you can look at a range of scenarios.
Yeah. No, this is where engineering supports science, because in my view, you have two ways that people propose science advance. You have stipulative, which is largely saying theory should be a certain thing. You have adventitious, which is you make discoveries because of technology. The increasing in computer capability to do simulation. But there are also increases in our ability to accurately represent what the past is telling us. That is another technological advance. And it has not received a lot of resources compared to the ability to make idealized conceptual advances about what we are saying about nature, not seeing what nature is saying to us. You have to have those two things working together. And you can be more powerful that way. I purposefully had my talk directed at the issue of what nature is saying to us, because that has not received sufficient attention. And I will fully admit that the people who work on that haven't really been effective in making their message. And the problem is philosophical, because that has to do with these fundamental assumptions people have about doing their things. But Hoshin has been trying to get his words in too, so yeah.
I think you pretty much actually attacked it, because I was basically going to say that, yes, you need to use all of the evidence from the past that you can get access to. But at the same time, you want to use everything that we've understood about the nature of the universe from all of that evidence, which is embodied in theory and models and so on. So my question was about whether there are ways that we're doing scenario analysis now which don't take advantage of this knowledge, that we could, in other words, that we could do better scenario analysis. So you talked about the probable maximum flood and how it was evaluated, and we can use past evidence to change that. But is there a way to get at a probable maximum flood which could be larger than that, because there are active changes going on in nature because of human effects and so on?
Well, I would go back to John Sawa's diagram. That you are trying to, science is a process that is basically, it's not circular reasoning, because this thing we're doing is actually a spiral, because every time you come around, you're coming to a new place, and that new place is enhanced understanding. And that enhanced understanding creates new opportunities in this part, which is the modeling part. But we also have to invest in this part. This part is where we're dealing with reality. There is no reality except the past. When I am saying these words to you, by the time you get them, it is past. So there is no reality other than the past. So to say that that reality is not important is to say, or to say the past isn't important is to say reality is not important. We're just going to have the figments of our imagination determine things. Now that's a philosopher talking there, but it's not, obviously, yeah. But yeah.
Would you say that this is the new scientific method?
Scientific method is a loaded idea. I mean, there's one guy who said science is just doing your darndest to figure things out, okay? And you use everything you can to do that. When my kids were in junior high school, they came home and said, "Dad, they're telling us this is the scientific method." And I said, "Look, I've been a scientist for 50 years. This is not what I do." So I do this kind of stuff, okay? And, you know, I love models, and because I don't do them, but they help me think about things. And so the whole process has to work. Remember, I said that the science is action, and it involves a community. Individual people who get scientific ideas commonly get known as crackpots, okay? They're independent of the whole community of scientists. So you have to have all of it working together. It has to be a community. That is one way that we pursue truth. Science is pursuing truth. Not having it is always the problem. What do you do with the truth that you have? You can't do anything with it. So we're always looking for more. And that's the beauty of science, because they're asking new questions all the time. It always is the question nature is presenting to you, and we're trying to figure out what that is.